Colleen Croniger, and today we're going to talk about fatty acid synthesis. Fatty acid synthesis occurs primarily in the liver. You do have some a little bit in the adipose tissue as well. For fatty acid synthesis, you excess calories from glucose, once the liver has replenished its glycogen stores, gotten all the energy that it needs, the end product of glycolysis is pyruvate, will go to acetyl-CoA and make citrate. Citrate, part of the TCA cycle, is what allows us to take the acyl moiety from the mitochondria out into the cytosol. This is called the pyruvate malate cycle. Citrate leaves, there's a transporter that allows citrate to leave the mitochondria. It goes through a lyase reaction to generate oxyl acetate. The malate dehydrogenase generates malate, and the malic enzyme generates pyruvate. Pyruvate now can re-enter the mitochondria to complete the cycle. In doing so, you notice that we're generating NADPH from the malic enzyme. The other place to generate NADPH for fatty acid synthesis is the pentose pathway. The first step, once you have the citrate being cleaved, it'll generate acetyl-CoA. Acetyl-CoA generates malonyl-CoA through the enzyme acetyl-CoA carboxylase. This is the rate-limited step. You can see I've got regulators all around it, and acetyl-CoA carboxylase is active in the fed state. In the fed state, when insulin is high, you're activating that phosphatase. And in this case, it's protein phosphatase 2A. That'll remove any phosphates and generate malonyl-CoA and increase malonyl-CoA for the next step. This is negatively regulated by its end product, so if you have a buildup of your fatty acids, that will inhibit it. If you're in the fasted state, glucagon will cause an increase of cyclic AMP and an increase of pKa, and that pKa can come in and it will phosphorylate acetyl-CoA carboxylase and inhibit it. So you've seen this pattern before. Insulin will dephosphorylate, pKa will phosphorylate. There are two isoforms of acetyl-CoA carboxylase. In the liver, you have ACC1. In the muscle, you have ACC2. They both do the same thing. They convert acetyl-CoA to malonyl-CoA. The difference is, in the liver, the malonyl-CoA can be involved in to make fatty acid synthesis, or it can be used to inhibit the carnitine shuttle. The muscle ACC takes acetyl-CoA to malonyl-CoA, but this ACC is on the mitochondrial membrane, where ACC1 is in the cytosol. This malonyl-CoA's only purpose isn't to inhibit the CPT. The regulation is slightly different too. In the liver, you have glucagon, which will increase cyclic AMP, which will increase pKa. That pKa will phosphorylate ACC1 and turn it off. In the muscle, it does not respond to glucagon. What it responds to is exercise. So you have an increase of AMP. AMP kinase gets activated, and that AMP kinase will phosphorylate acetyl-CoA carboxylase and inactivate it. So the liver responds to fasting, and the muscle responds to exercise. So once acetyl-CoA carboxylase generates that malonyl-CoA, the next enzyme that is used is fatty acid synthase. And fatty acid synthase has two regions on it that will bind an acetyl-CoA and a malonyl-CoA. And what happens with fatty acid synthase is that you're basically adding 2 carbons at a time from malonyl-CoA. So you have 2 carbons, then you're going to add 2 more carbons, going to add 2 more carbons, and so on, until you get to 16 carbons. That's palmitate. After palmitate, it needs to go to the ER. I'll draw it up here. It needs to go to the ER for modifications of palmitate to make other fatty acids. So it's a different compartment. This process, fatty acid synthase, is regulated at the transcriptional level by insulin and glucagon, and that really regulates the activity of the enzyme. But it's just a simple adding of 2 carbons at a time using malonyl-CoA.